I would like to thank the organizers for inviting me to this conference. And so today I'll be presenting my work, matrix completion framework for the Euclidean distance geometry problem. This is the work I did with my PhD advisor, Professor Ranjilai at Rensselaer Polytechnic Institute. So the outline of the talk will be, I'll briefly talk about the Euclidean distance geometry problem, and then give some background to this low-rank matrix recovery. And in that part, I will also show how we formulate this Euclidean distance geometry problem as a matrix completion problem, and some algorithm and results, and some conclusions and future work. So the problem that initially motivated us to consider was solving PDE on manifolds. And the standard way to do this type of problems is you already have the points which you discretize. So there are a lot of applications for this. For example, global recognition, what's the intrinsic distance to define on manifolds, classifying two manifolds, or if I have two shapes, could I understand the poses, compare the poses, or solving eigenvalue problems on different shapes. So this was the problem that initially motivated us to look into this problem. It happens that when this problem was being solved, what you had was not the points, but some incomplete pairwise distance information. Okay. So there is a lot of applications for the Euclidean distance geometry problem, from understanding the structure of proteins to sensor network localization to, for example, finding the location of cities and so on and so on. Okay. So just to show you some examples of the flavor of the work and the algorithm, on the left side here you have original image of a cow, which is sampled the total of 2,601 points. From this distance matrix, we sample about 1% of the distance matrix. And on the right-hand side, you have the reconstructed cow, which is what the algorithm recovers, having seen only 1% of the distance sample. Yes?
That'll depend a lot on how you sample.
Yes, yes, which is what I'll come about, yes. So, if you visualize this in MATLAB, this is what you see. So the left is the full distance matrix, but the right is the 1% distance matrix, which you see. So what I'll talk here is how does this low-rank framework work? What kind of sampling do you do, and what kind of guarantees do you have? That's the topic of the discussion. Okay. So since this is since everyone is familiar with this, I will not spend so much time. I'll briefly introduce this. But so given a set of points, we can define the distance matrix. And as already mentioned in the first talk, we can have this relationship in terms of the gram matrix, which I call X here. And the question is, if you have a full distance matrix up to rigid motion, could you recover the configuration of points? The answer is yes. But if I give you a partial distance matrix, could the configuration of points be recovered? That's the problem we consider under certain instances. Okay. So one way to regularize this will be to assume that if I have n points, which lie in r-dimensional space, and if the embedding dimension is way less than the number of points, I could minimize the rank with the constraint that I only know some of my distance samples. So that set omega is the sampling set I have. Okay? But this rank minimization problem is NP hard. So a work by Fazl was proposed in his PhD thesis, which is replace this rank by a convex relaxation, where the convex relaxation is this nuclear norm minimization. Okay? And I'll give some motivation why this is a good heuristic later on. So with this, you can solve this problem, minimize this low-rank approximation. But the fundamental question is, how are these two problems related? If we solve this relaxation, are you really solving the underlying true problem? So that's the question we try to answer. For example, in this recent paper, if you try to apply a low-rank matrix completion approach using the distance matrix was proposed in this paper. Okay? Another way to do this is to consider the gram matrix instead of the distance matrix. And the gram matrix is basically the same regularization. We put the centroid at the origin and ask if I have this relation between the gram matrix and the distance matrix, and if I consider this minimization problem, I want to answer the following two questions. The first question is, under certain conditions, could I show that this minimization problem actually recovers the underlying true gram matrix? Okay, that's the first problem. And the second problem is, if I am successful in some metric of success, how many samples do I need? And how do these samples come about? So this is the problem we study. Okay. So just to give some context why this low-rank regularization approach comes about, let me just give a perspective from the point of view of sparsity-based regularizations, right? So solving undetermined linear systems arises in many applications, but when we have infinitely many solutions, we don't have any good way to choose one. So one way to assume is that to say my underlying solution is sparse based on my application. So in that case, the natural optimization problem is to consider this L0 minimization problem with linear constraint. But this L0 minimization problem is also NP-hard. It has a combinatorial property. So what people have been considering, starting from the 1980s, was, can I consider a convex relaxation of this objective? Okay, and that convex relaxation turns out to be the L1 minimization. So L1 is just basically the L1 norm of the vector in consideration. So what does that do? So minimizing this L1 promotes sparse solutions. The nice thing is that this relaxation is a convex optimization program. And what people have shown is, under certain assumptions, this relaxation can exactly recover the true solution. Okay. So I'm not going to go through the detail, but the idea to show this type of equivalences actually rely on two techniques. The first technique is you put some strong condition on the measurement matrix A, right? Basically preventing from non-sparse vectors being in the null space. So that condition is known as the restricted isometric property condition. If you put this condition on the matrix, then you basically get this equivalence between the L0 and L1. Okay. What's the pro? So the pros are that this holds for many random measurement matrices. And once I fix this matrix, for any x, this equivalence holds. But the con is that for deterministic matrices, we don't know whether it holds. Checking whether this property holds is NP-hard. Okay. So an alternative analysis is to say, let me weaken my assumptions on this measurement matrix, and let me also limit the kind of underlying signals I want to recover. So that's the second idea, which is you loosen this RIP condition, and you limit, you lose universality. You don't say I can recover any signal. I'm going to put some conditioning on what I want to recover. So that's the second approach, which is the dual certificate analysis. So it's weaker condition, and the pro is weaker condition, but the proof is much simpler, and the con is you have a lack of universality. Okay. So with this setup, I want to motivate the low-rank regularization part, right? So this low-rank regularization became popular as part of the Netflix challenge, where Netflix challenged researchers to increase their prediction accuracy, right? So the original challenge had the following matrix, right? So you have, this is the users and the movies, and you have only observed 1% of that. And the goal is, based on what you have observed, to fill the rest of the matrix. Okay. So what does low rank mean in this context? In this context, it means that some users are related and some movies can be categorized together, right? So for example, we could think of this movie matrix as being made up of dramas, comedies, and sports. You can also categorize viewers into different age groups, meaning that the whole matrix might be big, but there is some information that will help us to make it low rank. Okay? So with that, we have this rank minimization problem, which we convert to this convex nuclear norm minimization problem. Okay? But again, the fundamental question is, how do you show that this convex relaxation is actually solving your original problem. Okay? So you could think of the nuclear norm as the sum of the singular values of a matrix. So you could think of the nuclear norm minimization as the L1 minimization on the singular vectors. Because the rank is counting the singular values. So you could think of the nuclear norm minimization as L1 minimization of singular vectors. This nuclear minimization program is a convex program, which is nice. As I said before, quite analogous to the L1 minimization case, there are two approaches. One is putting certain strong conditions on these measurements, and the other is this dual certificate analysis. And a couple of papers have shown that under certain conditions, this nuclear norm minimization problem is exact, meaning that by solving this relaxed problem, you are recovering the solution of the true problem you are solving. Okay? And the number of samples that we have is about nr log square n, where in our case, for example, where n is the number of points. Okay. So now with that, to go back to our fundamental problem, which is if I do this low rank regularization of my gram matrix, how do I convert it to an appropriate matrix completion problem? So before I discuss that, in general, in the earlier slides, what I was showing you was I was sampling an entry of a matrix. But you could generalize this low rank framework by considering in the following sense. If I'm expanding in an orthonormal basis, I could think of my measurements as being basically these expansion coefficients. So the sampling doesn't have to be just entry-wise. I could be sampling with respect to some orthonormal basis. Okay? That's precisely what was done by David Gross in 2010, where he basically generalized this low-rank matrix completion, where you are sampling with respect to entry. Now you are sampling with respect to some operator basis. And he basically showed that in that setup, you can basically get the same guarantee as the standard matrix completion problem. Okay. So without going much through the detail, this is where the assumptions come about. What kind of matrices could you recover? So you cannot complete any matrix because there are pathological examples, which I'll give example in the next slide. And that's basically captured by this definition of a coherence. So you could think of it as a conditioning of my underlying matrix. So this coherence condition basically looks up at the projection of these standard vectors onto the subspace U, in this case where U and V are the row and the column spaces. Okay? So let me illustrate this by an example. If I give you the first matrix, unless you see all the entry, there is no way to recover this matrix, right? Because everything is 0. So in this case, the coherence of this matrix is the maximum, and it's a pathological example. So I cannot expect this matrix completion procedure to recover this matrix unless it is the whole thing. Okay? Meaning that the information is really, really concentrated on a single entry in this case, right? The second example, if you consider this matrix, the coherence is the smallest. And one way to interpret this is to say that every entry is giving me equal information in some sense. So we prefer matrices with low coherence. Okay? So what are the key technical assumptions in matrix completion analysis? So one is the sampling scheme, some sort of random sampling that.
Say something. So, but in the first pathological case, that would be a very important. The quantity of information contained in that matrix is very high, whereas quantity of information contained in the other matrix is very low. So in a sense, you're saying, yes, there is no magic. We can complete fairly well those matrices that do not give us much information.
So if you choose this non-RIP-based analysis, you basically have no hope to recover this example one type of.
If we suppose that you had like a Netflix recommendation matrix that only had a 1, right? So Netflix could shed all of its films and just keep that film. Obviously, it's very precious to know something like this. I know it's not true, but if it were true, it would be very, very precious to know something like this. So there is this trade-off. This
Yes.
is sort of a magical technique in the sense that completes things for free, but it completes things for free as well as possible. Only with information content is fairly low.
It's true, yeah. I don't disagree with that. So the key technical assumptions are, first is the sampling scheme, meaning that later on when I'll briefly talk about the proof, you use techniques from random matrix theory to show that there is equivalence between the convex nuclear norm minimization and the actual rank minimization. We are solving a convex problem, so of course we use tools from the convex optimization theory, and this coherence is basically a limit which it avoids these pathological cases where the recovery fails. Okay. So now let me go back to the problem we were considering in terms of the distance matrix completion problem, right? So this is the problem we want to solve to complete the gram matrix. I have some distance samples. I have the centroid is at the origin assumption just to avoid translation ambiguity. The goal is, could I write this as a matrix completion problem that looks like this? Okay. So where S is, this S plus is capturing all these constraints I see here, the positive definiteness, the symmetry, and everything. Okay. So that doesn't seem too hard because I could basically construct a basis so that I could write this problem as if I'm sampling from some basis. Okay. So let me do that. So you can introduce this basis. So basically, with this basis, I basically can go from this representation to this representation. Okay. It turns out this basis is, you can check that this basis is not orthogonal. And we have the following problem. So the goal now is, I have something that looks like a matrix completion problem with respect to a certain basis, right? And what I want to say is, can I analyze this optimization problem and see how it relates to the true rank minimization problem? Okay. So there are a couple of challenges. The first that one could say, there is this restricted isometric property. Why can't you use this directly? You could construct counterexamples that show that this restricted isometric property doesn't hold. The intuition I want to give is whenever you have non-random deterministic setups, this restricted isometric property doesn't work because you can easily construct things that lie in the null space of this operator L. Okay. So one could say there is already a framework of matrix completion with respect to an orthogonal basis. Why don't you apply that? Well, you cannot apply that because this basis I showed you is not orthogonal, and we cannot use the existing theory. Also, we require that our solution satisfy these two properties. Okay. So the natural thing to say is, what I'm doing is I am expanding my basis, which represent my measurements, with respect to some dual basis. Okay? And my problem is basically I am sampling these measurements. Okay? That's the setup. So this setup basically says that I am considering a representation of x in this way, and the information I'm given is sum of these coefficients. Okay. So in the actual analysis, certain matrices become important. The first matrix is if you vectorize all these measurement matrices and form this 2H and H inverse, this play a crucial role. You can actually explicitly find this H and H inverse, which actually play a role in the analysis. Okay. We can write this more compactly by introducing what's called a sampling operator, which basically says I'm only going to look at the information I have in my sampling set. So with that, you can write this problem compactly in the following way. Okay, so actually, let me skip this. And so you can, the coherence conditions that you had before, we could also generalize them to this case. But the part I want to emphasize is this result. So now I can write my distance geometry problem in the following way, in this way. So this is basically the regularization part, and this is basically telling me the partial information that I have. Okay. And one of the results we show is if I assume these coherence conditions, and if I sample my entries at random with replacement, if I sample this number of entries, okay, then with very high probability, I'm going to recover my true solution. Okay, that's the main result. So it's saying that if you sample uniformly at random, more than this critical amount, then the convex relaxation is almost exact. So let me summarize, the result, because so the order is about nr log square n. So you are not really sampling the whole distance matrix. You are only sampling portion of it. I want to emphasize that the result is probabilistic. It's not deterministic. So what it's saying is, with very high probability, this Gram matrix is recovered. Okay. For example, Candace and Tao have shown that for the standard matrix completion problem, corresponding to this Netflix problem, you need this nr v log n. So our result is basically log n factor away from this optimal result. But the order is the same as the existing theoretical bound for matrix completion problem. So from the optimal lower bound, we are log n factor away. Okay. So what are the challenges? What's the difference between this problem and the matrix completion problem with an orthonormal basis? The challenge is that our sampling operator is not self-adjoint. And it turns out that in the proof, you have to bound the spectral norm of this quantity. And this is basically the main thing that prevents a new analysis, that prevents the existing analysis to be applied. And you have to come up with a new analysis. Okay, so the proof is basically uses the standard convex optimality conditions and the dual certificate approach. One thing I want to emphasize is that the proof uses concentration inequalities, and here is where the randomness comes in, because we are showing that certain things are bounded with very high probability. That's where this randomness probabilistic part of the proof comes in. Okay. Okay. So this concludes the analysis part of the talk. So, yes? To my understanding, the use of the dual certificate approach for this particular problem and this setup, to my knowledge, is our contribution. But if you can point me to that, then I'll look at it. Yeah, thanks. So we consider two cases for the algorithm. The first case is exact partial information. We factor the Gram matrix into PP transpose. Here we don't assume that we know the embedding dimension, so which is why I put Q here. Okay, so I put Q because I don't assume that my algorithm knows the embedding dimension. With that, I consider the constraint, which tells me the information I have, and this centroid is origin assumption into a linear operator. So basically, I have this AX is equal to B. So I consider this problem. We use augmented Lagrangian method. And we basically have two steps. You could solve this in many ways, but the way we solve it is we use the Barzili-Borwin gradient descent method, followed by just updating the parameters. Okay. We assume that if the distance entries are corrupted with Gaussian noise, you can also consider this problem. Now, this is no longer exact. And with that, the same setup as we have before with the augmented Lagrangian, with lambda as a penalty term can be given, and the same algorithm with slight modifications can be applied. Okay? So now let me show some of the results. So here, let me first describe how this, the setup of the numerical experiment. So I have a sphere, I have a cow, and I have a number of cities in the US. So what I'm given is I'm sampling from the distance matrix uniformly at random. So 1%, 2%, 3%, and 5%. Okay? And from that, I run the algorithm, and I try to see what it recovers. Okay? So I intentionally included this case, to show that sometimes it could fail when you don't have enough number of points, right? So this is basically that if you don't respect that threshold, of course it's not going to be able to recover this low rank regularization will not work. So as you can see, when you under this assumption that you have a uniformly random distance samples, you see basically you basically recover the ground truth. Okay.
So let me just make a remark there. So what you're recovering and quoting as a success is the overall shape.
Yes.
If you were to look inside these reconstructions, if you have few enough distances, there'll be parts of it that are not precisely located. There's just some instance.
Yes. Yes.
Okay.
Yes. One of the motivating, this analysis came as a result of this solving PD on manifolds and shapes that we were interested in. So I agree with you. If you look close enough, you might see artifacts. So which is, for example, for what I want to show for the noisy case, right? So for the noisy case, it still looks like a sphere, still looks like a cow, right? But if you look close enough, there are some artifacts. This is part of the work my advisor did using this approach, to solve PDEs on manifolds. Okay. So compared to the previous algorithm, which was considered here, namely their algorithm doesn't factorize the gram matrix. That's the main difference. We use the same technique, except their algorithm doesn't factor the gram matrix. This algorithm is fast. Okay. So to summarize, in the framework of uniform distance samples, this matrix completion approach gives you some theoretical guarantee, which basically informs you that as long as you have some optimal number of samples, you will be able to recover the underlying object with very high probability. But of course, in the distance geometry problem, the framework is not only, what we have is not, uniform distance samples. We have non-uniform distance samples. So that needs to be taken account into the theory. So this is an opportunity to consider low rank regularization in terms of non-uniform distance samples. The analysis for noisy data and data with outliers is an opportunity. Currently, this low rank regularizations approach, the theoretical analysis or the guarantees suffer a little bit when you consider the case with noisy and outliers, which is the case with real data. So this needs to be considered. There is also analysis of other convex and non-convex relaxations, and using the techniques here to see what can be said. So the idea here is to say in a certain instance, where you have this ideal case of a uniform sample, you could do this, but the goal is to use this framework in a more realistic setting. So the code is available at my GitHub page, and all the codes and all the results are there.
So why did you call it non-convex solver? You called your code non-convex problem solver.
Because I factorize my gram matrix into this PP transpose.
Okay.
Yeah, that's why. The previous code didn't factorize that.
I get it.
Yeah.
Okay, thank you.
Yes.
So can you go back to the pictures?
Yes. Oh, sorry. Other way around. Okay.
So when you look at these reconstructions, a key ratio is the number of distances to the number of points. So in the case of 1%, what is that ratio?
So the sphere has about 1,002 points.
And how many distances are in that reconstruction? It's 1%, so it's about 1,000 distances.
I think so, yeah. So about 1% of that whole distance matrix.
And so these distances are chosen randomly.
Yes.
So you have a random. This is basically a percolation problem, which is this is a physics talk. But the key thing is that if you have the ratio n over r greater than a certain threshold, then you will get a rigid structure that percolates across your sample, and you have to have that to reconstruct the overall shape. If you're below that threshold, that won't happen. So as you go to 2%, you're well above the threshold, and you get percolating structures that almost cover the entire graph. However, within the graph, there are pieces of it that are flexible, and so that's the regions that are not precisely determined. So you could do an analysis based on rigidity theory that can tell you what this ratio of distances to points needs to be for any given system and any embedding dimension, so that you can be sure the overall shape will at least have some rigid structure for a given case. It's interesting just to think about it.
Okay. Yes.
So in your algorithm, you said you didn't assume the embedding dimension. You
Yes.
called it Q.
Yes.
How do you handle that algorithmically? I'm not sure. Maybe you mentioned it in your talk. But
Yeah. So in the reason we don't want to assume is we don't want to think that the embedding dimension is given to you.
So do you update it somehow? Like, do you start with a value of Q and then change it at some point, or is it a parameter of the algorithm?
It's a parameter of the algorithm.
So the user would say, I think Q should be 10.
Yeah. So Q is 10. For all of these results, I use Q is equal to 10.
Oh, you did use Q. I just picked that up.
Yeah. Q.
Okay.
I didn't want to, because the results definitely improve. If you choose something closer to the actual embedding dimension.
Yeah.
But for the application we're considering, in addition to this in the shape matching, we don't want to actually think the point cloud is embedded in 3-dimensional
Right.
4. So for that reason, Q is 10.
And then how do you get these images then out of that? At the end you get a solution which is actually rank 3 or rank 2?
Yeah. So we still all these plots are basically corresponding to that Q, and not to the actual dimension.
Okay,
Yes,
okay.
yes. So if I can tell you more details
Sure,
about
sure.
that process. Yes.
Okay, thank you.
Yeah. Oh, sorry.
You assume that the real objects have some properties, that they are kind of sparse. Have you encountered some objects which don't fulfill this assumption?
Sparse, you said?
You mentioned that today.
So the main theoretical assumption here is that this coherence condition, meaning that you cannot have all the information concentrated to a certain region, right, in terms of the shape. If you don't have that, so this is where the theory and the algorithms differ. Algorithms still work in this realm where the coherence condition don't hold. But we know we don't have any theory right now in matrix completion that basically says if I remove my coherence, can I show my results? No. So it's a theoretical assumption. The algorithm is forgiving. The algorithms are forgiving to that condition. But the theory, we cannot prove it without this coherence assumption. Basically, you have to do what I said, which is put a very strong condition on the matrix, which is that RIP condition, which if you are doing something like the distance geometry problem, doesn't hold.
Any other question? Oh, yes.
You said you used the BB algorithm.
Yeah.
Why that particular?
It's because I already had a code for it. Yeah, that was the reason. But nothing. You could use anything for that part.
So let's text the speaker.